Good morning, everyone. My name is Lubna Blaidi, and I am pleased to present our work entitled Automated Fabric Defect Detection Using Unsupervised Feature Learning with Deep Autoencoders. This research was conducted in collaboration with IFF Biljadid and Adil Tannoush at Sultan Moulay Slimane University in Morocco. The textile industry is one of the largest manufacturing sector worldwide, and ensuring fabric quality is critical challenge. Traditionally, defect detection has relied on manual inspection, which is slow, costly, and prone to human errors. Even small defects, such as holes, stains, or bars, can reduce product value and harm customer satisfaction. This motivates the adoption of computer vision and artificial intelligence to automate fabric inspections. Problem statement. However, existing solutions face important limitation. Manual inspection is subjective and inconsistent. Traditional computer vision techniques rely on handcrafted features, and they often fail with complex textures or illumination changes. This highlights the need for a robust, automated, and scalable method to detect textile defects. Objectives. Based on this problem, we define the following objectives. First, to design an unsupervised defect detection approach that does not require labeled data defect images. Second, to use convolutional autoencoders for learning normal fabric patterns. Third, to detect three common defect types: holes, stains, and bars. And finally, to move toward the automation of quality control in textile industries. The dataset includes 180 defect-free images for training and 120 images for testing, divided equally among three types of defects: holes, stains, and bars. As shown here, there are 4 examples of images for normal fabric, for hole, for example of bar on tissue, and stain. Before training, images undergo processing. They are first resized to 128 by 128 pixels, then converted to grayscale. Pixel values are normalized between 0 and 1 to stabilize training. Finally, simple augmentation such as horizontal and vertical flips increases dataset variability. This pipeline ensures consistency and improves the model's generalization. The proposed model is convolutional autoencoder. The encoder compresses input into a low-dimensional latent space, which the decoder reconstructs the original images. Training is performed using mean squared error as the last function and optimized with ADAM. The goal is for the model to accurately reconstruct defect-free fabrics while producing higher errors when defects are present, of course. For defect detection strategy, at inference, the strategy is straightforward. First, the input image is reconstructed by the autoencoder. Second, we compute the reconstruction error between input and output. Finally, an error map highlights the defect location. As shown here, the model reconstructs a smooth fabric, but the error map clearly localizes the hole in red. This provides both direction and localization. Experimental results. Here we present the quantitative. the results for whole defects. The model achieves a precision of 96% and an F1 score of 95%. For bar defect precision is a 91% with an F1 score of 89%. Stain detection is slightly weaker with an F1 score of 87% due to subtle intensity variations. Overall, the approach demonstrates robust performance without requiring labeled defect data. Yes. We move to discussion and future work. This method has clear strengths. It works without labeled defect images, and it is effective for well-defined defects like holes and bars. However, there are limitations. The dataset is relatively small. Only grayscale images were used and stains remain challenging. In the future works, we plan to extend the work to RGB or HSV channels for richer representations. We explore advanced models such as variational autoencoders. Explore advanced models such as variational autoencoders, GANs, and vision transformers, and investigate real-time deployment for industrial applications as well. In conclusion, convolutional autoencoder are a promising solution for unsupervised textile defect detection. The method achieves strong performance in detecting holes and bars and provides valuable insights for quality control. This work represents a step toward the digitalization and automation of textile inspection within smart manufacturing environments. So thank you very much for your attention. I will be happy to answer your questions, and you can also contact me on this address. Thank you so much.